Hi, hello everyone. This is your educator, your tutor, your friend, Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. Do watch this session. If you like it, do press the like button. Share it with your other friends who are preparing for their boards and competition as well. Alright, subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Okay? Now, without any delay, let's get started with today's session. We were doing electrostatic potential and capacitance, and this is lecture number 3, where we'll be discussing about equipotential surface and along with that relation between field and potential. Okay, equipotential surface, if you remember last time when we were doing potential due to dipole, I told you at the equatorial plane, the potential at each and every point is 0. That's why we call it as equipotential surface. Why? Because the potential is same everywhere, right? I hope you remember. So equipotential surface is basically a surface at which potential is same everywhere. Last time what we saw was, suppose there is positive charge, there is negative charge, it was a dipole. At the equatorial plane, if there is a plane something like this passing from the center, from the equator of this, right? So at this plane, the potential will be 0. Potential will be same at each and every point, so we call it as equipotential surface. But it is never necessary that equipotential surface will be a plane surface or a plane sheet. No, it can be a sphere also. It can be a cylinder also. It can be of any shape. Alright? It depends on the electric field present at that area, in that particular area. Like suppose, now suppose there is a positive charge. If I enclose this positive charge with a sphere, let's say, it is not a circle, it's a sphere, alright? Now this positive charge will be having electric field lines, or let's say the radius of this sphere is r. Now at this particular point, there will be some potential. At this particular point, again this is at a distance r because it's on the surface and this is radius. At this particular point and at this particular point, at any point on the surface, if I ask you the potential due to this charge, how much will it be? It is distance r from the charge, so this will be kq by r. Here at point 2, again it will be kq by r. Correct? At point 3, again it will be kq by r. Why? Because the distance between this point and the charge is r everywhere. Any point you take on the surface, the potential will be kq by r. At every point on the surface, since the potential is same, we call it as an equipotential surface. So for a sphere, the equipotential surface, for a charge, for a point charge, the equipotential surface is a sphere enclosing that charge. Clear? For a point charge, equipotential surface is the sphere enclosing the charge, where this point charge is at the center of the sphere. Okay, this is a sphere. This is a point charge. All right, at the center. This is equipotential surface for this point charge. If you want, you can write down. For a point charge, the equipotential surface is the sphere enclosing that point charge. That point charge should be at the center of the sphere. That also you have to mention. Alright. Now, suppose this is a line charge. It's an infinite line charge. How will be the equipotential surface for this line charge? Again, if you think properly, the electric field lines will be like this, or forget about the field lines, that we'll talk about it later. Now at this particular point, if I want to find the potential, if this point is at a distance r from here, it will be kq by r. Where else the potential will be kq by r, can you tell me? At any point which is at a distance of r from this line, and from the line we take distance perpendicularly, correct? So from this line, if I take a point here which is at a distance r, the potential will be kq by r. This side at a distance r, if I take any point, the potential will be kq by r. Anywhere here, if I take a point at a distance r, it will be kq by r. Correct? If you join all these points, it will form a cylinder. It will form a cylinder. So for a line charge, the equipotential surface will be a cylinder where this line charge will be on the axis of the cylinder. For a line charge, the equipotential surface will be the cylinder where this line charge will be on the axis of the cylinder. Again, this is the equipotential surface. Clear? It's a cylinder. Equipotential surface for the line charge. This line charge is at the axis of the cylinder. Clear? Note it down. Now, if I ask you properties before that, suppose there is an electric field like this. It's a uniform electric field. It's a uniform electric field. How will be the equipotential surface? Equipotential surface. It will be perpendicular to the electric field lines. Clear? The surface will be like this. You can make it's a plane like this. All right. At each and every point, the potential will be same. All right. Very easy to understand how these electric field lines are like this. Let's suppose there is a very big positive charge here. The electric field lines are like this. Now from this positive charge, this distance is same. Or let's say there is a charge like this. From this, the electric field lines are going like this. Correct? From this charge, this sheet, since it is like this, perpendicular to the electric field, this sheet will be at the same distance. So for a uniform electric field, the equipotential surface will be perpendicular to that field. Clear? Anyways, the equipotential surface will always be perpendicular to the field. We'll see it now. The potential difference between any 2 points. Now these are the properties of equipotential surface. The potential difference between any 2 points on the equipotential surface is 0. Right? Why? Because the potential at each and every point is same. So if you take the difference, it will be 0. If this is an equipotential surface, this is point A, this is point B. Potential at A will be VA, potential at B will be VB. Since it is equipotential surface, both VA and VB will be same, so this difference will come as 0. Clear? This is the first property. Second, work done by electric force on moving a charge on equipotential surface is 0. Now this, suppose this is a charge. Here, let's say, no, that is not a charge. Suppose there is a charge, Q. This is point A. We have to move this charge to point B. The work done on moving this charge from A to B by the electric field will be, or electric force will be 0. Why? Very simple to understand. If you remember by definition, VA minus VB or VB minus VA, if we have to take charge from A to B, VB minus VA is equal to work done in taking the charge from A to B divided by the charge. Remember the first lecture of potential? VB minus VA is equal to work done in taking the charge from A to B divided by the charge. Now here, this is what? Delta V. Potential difference on the equipotential surface is 0. If this is 0, work done from A to B, or we can write this as work done will be equal to delta V into Q. Delta V is 0. So work done will also be 0. Now this is the work done by the external agent and work done by the electric force. will be equal to minus work done by external agent. If this is 0, this will also be 0. Clear? Work done by electric force on moving a charge on equipotential surface is 0. By definition, it came. Logically also you can understand. Since the potential is same everywhere, the work done will be 0 only. Fine. You can write as delta V is equal to work done by external agent divided by Q. Now, delta V is equal to 0. Therefore, work done by external, or here, the same way you can write, from this, work done by external agent is equal to delta V into Q. Delta V is 0, therefore work done by external agent is equal to 0. Work done by electric force is equal to minus work done by external agent. So this is equal to 0. Clear? Next. Field lines and equipotential surface are mutually perpendicular. Field lines and equipotential surface are mutually perpendicular. Just now I showed you that is true. Why? Because if it will not be perpendicular, the surface will not be equipotential. Very simple. See, there is a charge Q. From this charge, the electric field lines are coming radially outwards. Correct? If I want the potential to be same at all the points, I will have to make a sphere around it, so that the distance from here to here remains the same everywhere. Correct? Now suppose if I do not make a sphere, let's say, electric field lines are coming like this. If I make a plane surface, why this plane surface will not be equipotential surface? You see, from here to this, there will be, the distance is different from this to here. This is more, this is less, this is more, this is again more, this is again more. If the distance is more, electric field not, if the distance is changing every time, electric field will be changing, kq by r square, right? And if the distance is changing, potential will also be changing, kq by r. Here the potential will be different, 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 right? But if we make this surface perpendicular to the electric field lines, the distance from this charge to this surface will always be same. Clear? Now, if you want to understand this from the formula, later on, once we will see the relation between electric field and potential, then we will get a formula as delta V is equal to minus E dot dx, minus E dot delta x. This is the basic relation between potential and electric field. This will derive in this session only later on. Alright, from here, now suppose if delta V is 0, if this becomes 0, what does this mean? E dot delta x is equal to 0. If this becomes 0, this means that this is 0. Now these are vectors. This is a dot product. If two vectors dot product is 0, what does this mean? Either this E is 0, either the electric field is 0, or electric field and this delta x are having 90 degrees angle between them. That means this electric field is perpendicular to surface. Delta x, how it came? If it is a surface, this is point A, this is point B, this will be delta x, correct? In moving from A to B, electric field is perpendicular like this. Then only we can say electric field is perpendicular to delta x. If electric field is perpendicular to delta x, that means electric field is perpendicular to the surface also. Delta x is parallel to the surface, on the surface. So if from here we can derive that electric field is perpendicular to delta x, correct? And delta x is on the surface. So electric field is perpendicular to the surface. So field lines and equipotential surface are always mutually perpendicular. Clear? All right. Next. Next it says, two equipotential surfaces can never intersect each other. Understand? Two equipotential surfaces can never intersect each other. Why? Now suppose there is one equipotential surface like this. Let us make it intersect. Let us intersect them and then see what comes. Okay. Suppose one more surface is like this. Clear? This is equipotential surface. That means the electric field lines passing through this equipotential surface will be perpendicular to it like this. Correct? For this equipotential surface, this one, this, the electric field lines will be perpendicular passing through it, means electric field lines will be going like this. Correct? Electric field lines will be like this. Now, see, the electric field lines are crossing each other. If you make electric field lines like this, electric field lines are crossing each other, and electric field lines can never cross each other. If you remember the very first lecture of the electric field lines, in the first chapter, electric field lines can never intersect each other. Why? Because if they do so, at one point there will be two directions of electric field. At this point, electric field is here also, electric field is here also. At a single point, two directions of electric field can never exist. It's not possible. That is the reason two equipotential surfaces can never intersect each other. Clear? Note down all these points. Important. In boards, they will ask. Only important from board's point of view. Next, equipotential surface for a dipole. There is a dipole. If we want to make equipotential surface, how will it be? In the last lecture, I just told that this equatorial plane will be an equipotential surface, but there can be a lot of equipotential surfaces, thousands, infinite equipotential surfaces you can make. Let us make it. For making equipotential surface, first thing what you have to do is make the electric field lines. If this negative charge was not there, electric field lines would be radially outwards, correct? But now this negative charge is there, this line will move towards it, right? Let us make the electric field lines. It will be like this from here. Correct? Now see, if I want to make the equipotential surface for this, equipotential surface at the center, if you want to see, it will be perpendicular to the electric field lines. That means like this. How we know that this is perpendicular? Simple, make a tangent at this point for this line. It will be straight. For this line, the tangent at this point will be straight, horizontal. At this point, the tangent on this electric field lines will be straight, horizontal. And a perpendicular line crossing all the horizontal tangents will be straight like this. This is the equipotential surface at the middle. Because at the middle, the lines are nearly horizontal, right? As you move this side, these lines will start making curve. Now this is a surface, these are not lines. 3D surface this is, okay? If you close it, it will be something like this. This side also will be like this. Clear? This blue one is the equipotential surfaces. If you want, you can note it down, you can draw it. If you want a clear image, this is the equipotential surfaces. Now here, just see one thing. This charge is not at the center. This, if you consider this as a sphere, this charge is at a side. Why? Because the electric field lines are not coming out radially. They are more bent towards it. And these all surfaces are 90 degrees to the field lines. Clear? So in the exam, while making, if it comes, make sure this charge you do not make at the center. These circles, if you see here, see the gap is less, here the gap is more. This side the gap is less, this side the gap is more. Done? So with this, we complete the equipotential surface. It's no rocket science, it's a very simple thing. A surface at which at all the points, a surface on which at all the points the electric potential is same. It can be any value, but same. Now, relation between field and potential. The important topic for today is this. relation between field and potential. Now suppose there is a positive charge at some distance r. There is a point P. I want to write potential, I want to write electric field at this point. What it will be? E is equal to KQ by R square. At the same point, if I want to write potential, okay, electric field will be outwards. Potential is a scalar quantity. V is equal to KQ by R. Correct? One R difference is there in the denominator, right? But this is vector, this is scalar. So there is more difference also. We'll get to know about it. Now, so one more thing what you have to understand is, as we move towards the electric field, the potential keep on decreasing. Let's see. Suppose this is a positive charge. Electric field lines will be like this. Let's say there is a point P, or let's say there is a point which is at 1 meter from here. Okay. Another point is at 2 meters from here. All right. Third point, let's say here, it is at 3 meters from here. Positive charge, electric field line will be going outwards, okay, in this direction. Now, can you tell me potential at this point? At this point. If I want to write the potential, what will be the potential? KQ by 1. Correct? Potential at this point? KQ by 2. Right? The distance between charge and this point is 2 meters. At this point, KQ by 3. Can you tell me which one is the smallest and which one is the largest? This is the largest, this is smaller than this, and this is smaller than this. Correct? Now see one thing, notice one thing, as we are moving towards the electric field line, the potential is decreasing. Is it always true? Yes, it is always true. If I take a negative charge also, let's say, electric field line will be towards the charge. Correct? Electric field line will be towards the charge. If I take these same 3 points, let's say, this is at 1 meter, this is at 2 meter, this is at 3 meter. From this charge, all right, this point. At this point, potential will be minus KQ by 1. It's a negative charge. Potential is a scalar quantity, it comes with a minus sign, right? Here it will be minus KQ by 2. Here it will be minus KQ by 3. Are you yes or no? At this point, which is at a distance of 3 meters from here, the potential will be minus KQ by 3. At this point, which is at a distance of 2 meters from there, it will be minus KQ by 2. And at this point, which is at a distance of 1 meter from this charge, it will be minus KQ by 1. Tell me which one is the smallest and which one is the largest. See, this is the smallest. This is the largest. Why? Because the negative sign is there with it. This negative sign does not indicate the direction. Potential is a scalar quantity. It comes in the magnitude. Magnitude wise, if you see all the three, this is the largest and this is the smallest. Again, the electric field line is going like this. Electric field line is going like this, and as we are moving towards the field line, potential is decreasing. This is always true, whether you see for the positive charge or a negative charge. So what you have to note down is, electric potential, very important this is, electric potential always decreases on moving in the direction of electric field line. Clear? Electric field line, electric potential always decreases in the direction of electric field line. Done. Now, we have to find the relation between field and potential. There can be two cases. One, the field is uniform, one, the field is non-uniform. Okay, so two relations will come, one for the uniform field, one for the non-uniform field. Again, both the relation will be nearly same. They come from each other only. Let's see. If electric field is uniform, suppose there is a uniform electric field, there is a charge present here. Now on this charge, a force is being applied like this. If this is E, electric field, force will be applied here, correct? Now let's say this is at some point A. I have to move it from point A to some point B. From this point to this point I need to move. So from this point to this point, this distance, this, if I take in vector, I can take it as delta x vector. It has moved delta x vector. Vector means direction is from A to B, delta x is the distance moved. Clear? Delta x vector. Now here I have to find out potential difference from A to B. Delta V from A to B. Delta V is what? Delta V is what? Delta V is equal to work done from A to B. From A to B per unit charge. Where this delta V is VB minus VA, correct? VB minus VA is equal to work done on moving this charge from A to B divided by the charge. The charge is small q, let's say. Correct? I hope this is clear. Now, here if you see, this QE force is this side. So the QE force itself is taking this charge from A to B. What is the need of external agent? External agent is not required only, is it? No. By definition, this change in potential is work done in taking the charge from A to B per unit charge by taking kinetic energy constant without the change in kinetic energy. Without the change in kinetic energy, correct? Always remember, kinetic delta KE should be 0. The change in kinetic energy should be 0 because some work will be done in changing the kinetic energy. So we will not get the correct potential. Alright, delta KE should be 0. How will delta KE will be 0? When the net force on this charge will be 0. If we make the net force on the charge 0, then the change in kinetic energy will become 0. Why? Net force is 0. Correct? There will be no change in velocity. No change in velocity means no change in kinetic energy. Clear? So for making this net force 0 on it, the same force will be applied by external agent opposite to the electric force, QE. Now see, net force is 0. This charge will go from A to B without the changing kinetic energy slowly to B. Clear? VB minus VA is equal to work done from A to B per unit charge without the change in kinetic energy. Now understand, here only I'll write VB minus VA is equal to work done from A to B divided by Q. Work done from A to B I have to take out now. What is the work done? How we take out the work done? Work done is the dot product of the focus and of the force and the distance. F external dot delta x, correct? F external vector dot delta x vector. This is work done. Work done is a dot product between F and x, correct? Now here, if I want to write work done from A to B by external agent I am writing. So this will be force by external agent dot delta x. Now see, delta x direction is in this side and this force by external agent is opposite side. So this I will take negative, this I will take positive. Minus QE into delta x, correct? Minus QE dot delta x. This force is negative to this electric force. correct? So force by external agent is basically minus QE, right? Delta X is plus delta X. So minus QE dot delta X. Right now I am not opening this dot product. I am not writing cos theta further. Okay, everything is in vector form only. This is scalar, this is vector. Okay. Why I am not opening this? Because here I have taken angle as 180 degree. Here these both are in opposite directions, correct? But it can be any angle. Theta can be anything. That's the reason right now I have kept it in this way only, dot product. Okay. So this will be minus, okay, till here only. Right? Q is scalar. Minus Q E vector dot delta X vector. This is work done from A to B. This VB minus VA is equal to this work done from A to B divided by Q. That means minus Q E dot delta X divided by Q. Q and Q will be cancelled. We will be left with minus E vector dot delta X. That is equal to, this is what? Change in potential difference. Change in potential. This is potential difference, delta V. Delta V is equal to minus E dot dx. Delta V is equal to minus E dot delta X. Very important. Very important. This relation is very important. Okay. So this relation comes when electric field is uniform. This delta V is equal to minus E dot delta X. These both are vector. This is a scalar. Next. Now when electric field is non-uniform. Non-uniform means electric field is something like this. Let's say. Okay. Or let me make it. Now, there is a point here, there is a point here, there is a point here. Here, electric field is more, here the electric field is less, correct? We did this where the electric field will be more, where these electric field will be more dense, or the space between the electric field lines will be less. There the electric field is more. Here it is more, here it is less, here it is less. So everywhere it is changing, it's non-uniform. It is non-uniform. Now we know delta V is equal to minus E dot delta X. But here it is not uniform. For a very small distance, dx, can I consider the electric field as uniform? Although for this entire thing it is non-uniform. But for a very small distance, dx, can I consider it as uniform? For this small thing, if you see, it is uniform only. Here also, if I consider a very small dx, for this, if I consider this small dx, if I move in this small dx, for this small distance, the electric field I can consider it as uniform, right? So for this small distance, the change in potential will also be very small. So change in potential will be dV, that is equal to minus E dot dx. Clear? For this very small dx, I have considered this electric field as constant. For this very small dx, I have considered this electric field as constant, and for this small dx, the change in potential will be dV. So we got dV is equal to minus E dot dx. Clear? Again, this is very important. Very important. Always remember this. Alright? This is the main relation between electric field and potential. From this relation only we usually get this relation. Because if I integrate this, if suppose electric field is really constant, and if I integrate this, we'll get delta V is equal to, let's say I'm integrating it, dV from VA, from B to A, from A to B. That is equal to minus, if E is constant, here we'll get x2 minus x1, correct? Dx, if you integrate, you will get x, limits will be from x1 to x2, or a to b x2 minus x1, this will finally become as delta x, and this dv from a to b, va minus bb, this will finally become as delta v. From here only we get this formula, delta v is equal to e dx, delta v is equal to e delta x, correct? So this is the main formula. This is whether the electric field is uniform or non-uniform, everywhere this is applicable. What we have done here is, for a very small part, we have considered electric field as uniform. It will be, right? So we have broken this into infinite small parts, into infinite small distances, and then we have found out potential for those small points, infinite points, and we have added. Adding means integration. Integral delta v is basically integral minus e dot dx. Delta v is basically integral minus e dot dx when the electric field is non-uniform. Now, if we know the electric field, we can find the potential. But can we find electric field if we know the potential? Okay, before that, let's see in 3D space. Electric field I can write as Ex I cap plus Ey j cap plus Ez k cap. Are yes or no? Electric field vector I can write like this. Okay. Dx vector, dx I cap, let's say dr vector, dx I cap plus dy j cap plus dz k cap. You remember it this way. Instead of e dot dx, remember e dot dr. If x is there, then people only think in x. It can be any 3D, right? So dr is dx I cap plus dy j cap plus dz k cap. Delta v is equal to, or dv is equal to minus e dot dr, correct? So I can write it as minus ex I cap plus ey j cap plus ez k cap dot dx I cap plus dy j cap plus dz k cap. Are yes or no? Dot product of two vectors in 3D. I hope you know this. What will it come? Minus ex I will multiply, j will multiply, the term having k will multiply, right? So this will be ex dx minus ey dy minus ez dz, correct? This is dv. dv is equal to minus ex dx minus ey dy minus ez dz. Then now, if I do partial differentiation of this, if I do partial differentiation of v with respect to x, then with respect to y, then with respect to z, what does this mean? This means that we are changing in x, keeping y and z constant. Then we will be changing in y, keeping x and z constant. Then change in z, keeping x and y constant. That is what partial differentiation is. So from here, partial differentiation is represented by dou. Dou v by dou x will be equal to minus ex. If I differentiate it partially, dou v by dou x will be minus ex. Dou v by dou y is equal to minus ey. See here. Because if I am differentiating this with respect to x, keeping y and z constant, this will be this dx, this will be ex. Here y is constant, dy will be 0, z is constant, dz will be 0, these two will become 0, right? When I am differentiating with respect to y, Here we'll get minus Ey. This will become 0, this will become 0. Why? Because x is constant, z is constant. So if x is constant, dx is 0. If y is constant, dz is 0. So these two will be 0. If I am differentiating with respect to z, so dv by dz, right? Dou v by dou z is equal to minus Ez. Why? X and y are constant now, so dx will be 0, dy will be 0. Clear? The differentiation of this and this, they both became constant, this will be 0. Fine. Now, from here, I can write Ex is equal to minus dou v by dou x. From here, I can write Ey is equal to minus dou v by dou y. From here, I can write Ez is equal to minus dou v by dou z. We got Ex, we got Ey, we got Ez. See, E vector is Ex I cap plus Ey j cap plus Ez k cap. So from here I can write E vector as Ex I cap. Ex is what? Minus dou v by dou x. Minus dou v by dou x I cap. Plus minus dou v by dou y j cap. Plus minus dou v by dou z k cap. This is E vector. This looks scary, but this is very easy. Try deriving it on your own. This looks a bit scary, right? But it is very easy. Once we'll do questions, this dou v, dou x, dou v, dou y, this looks very difficult, right? It's not. Once we'll do questions, you'll understand it is very easy. Note it down till here. Okay. So now see, if you know potential, you can find electric field. Let's see the questions. Two plates are kept at a separation of 1 meter. Electric field between them is constant with a magnitude of 10 Newton per Coulomb as shown. Two plates are there, kept at a separation of 1 meter. Electric field between them is constant, given to be 10 Newton per Coulomb. The potential on the first plate is 30 volts. Find the potential on the second plate. How do we do this? This we know, we have to find potential there. Delta V is equal to minus, okay, one more thing, to make your questions easy. Here, you would have written this. Delta V is equal to minus E vector dot delta X vector, right? But what you have to remember, this is good for exams, but what you have to remember is delta V magnitude is E delta X. E dot delta X. Don't see the sign. Clear? The magnitude of delta V will be E dot delta X. Fine. How will the sign come? What you have to remember is delta V, potential. Potential decreases on moving towards electric field. Clear? Potential decreases on moving towards electric field. Don't have to remember this minus sign and all. Only remember the magnitude. Okay, now see. Here, if I just write the magnitude, delta V is equal to E into delta X. E is this. Delta X is this. Okay. So, and the angle between E and delta X is 0. We are moving in this direction only. Cos 0 is 1. So I can write E delta X. So this will be E is 10, delta X is 1 meter. That is equal to 10 volt. That is the potential difference. Do not write that the potential on this plate is 10. It is the potential difference, right? So that means the potential difference from here to here is 10 volt. So on this plate, there are two possibilities. Either the potential will be 20 volt or the potential will be 40 volt, correct? The potential difference is 10 volt, E into delta X, 10 into 1. Now, the chances are on that plate, the potential can either be 20 or 40. What will be the answer? What will be the answer? Answer will be 20. Why? Potential decreases on moving towards electric field. Here we are moving towards electric field. Can the potential be 40? Never. We are moving towards electric field, right? Potential will be less. So the answer is V at second plate is equal to 20 volt. All right. All right. You can do another way also. Delta V is equal to minus E vector dot dx vector. You can do this way also. You can do this way also. This delta V is VB minus VA. That means V on second plate minus V on first plate is equal to minus sign of again 10 into 1, cos 0 is 1. V on first plate is 30, Vs minus 30 is equal to minus 10. Vs is equal to 30 minus 10, that is equal to 20 volt. You can do this way also, not a problem. But this I feel is easier. Alright. Next. 4 points are marked in a region of uniform electric field of 10 volt per meter as shown. 10 volt per meter, this is also volt per meter, this is also unit of electric field. How? Delta V is equal to minus E delta X, or let's say we found that Ex is equal to dou V by dou X, correct? This is volt, this is meter. E is volt per meter, so that is also 1 unit. Newton per coulomb is also 1 unit, volt per meter is also 1 unit of electric field. Now 4 points are marked in a region of uniform electric field of 10 meter as shown. This is uniform electric field. These are 4 points marked, shown here. Okay. The points are shown in a square. It is a square, 1 meter, 1 meter, 1 meter, 1 meter. Find the following: VA minus VB, VC minus VD, VA minus VD, and VC minus VA. These 4 things we have to find. For VA minus VB, again it is very easy. You can just see and do it. Oral question. VA minus VB, electric field is 10 volt per meter. As you move 1 meter, 10 volt difference comes. Fine. VA minus VB, 1 meter, 10 into 1, right? E into delta X. Delta X and E both are in same direction. Cos 0, 1. So directly E into delta X we can do, right? E delta X, that is equal to 10 into 1. Or directly I will just multiply instead of writing the formula. 10 into 1. That is 10 volt. Correct? Correct. VA minus VB. But will it be plus 10 or minus 10? Again, no need to remember that minus sign. Just multiply, write the magnitude, then see. On moving towards the electric field, the potential has to be decreased, has to reduce. So VA will be more than VB. VA minus VB only we are doing. So it will be plus 10 volt. Clear? Now, VC minus VD. VC, VD. Now from here we are coming here. Again, this is 1 meter, E is 10 volt. So 10 into 1, that is equal to 10, not a problem. But whether it will be plus 10 or minus 10. Again, see, this time we are moving from C to D. We are moving opposite to electric field. VD will be greater than VC, correct? If you move like this, on moving towards electric field, potential decreases. That means VC will be less than VD, right? If VC is less than VD, forget about this. If VC is less than VD, what will be VC minus VD? Minus. A minus sign has to come here. Minus 10 volt. Clear? Here, VA minus VD, delta x is 0. On the same line both are, it will be 0. Fine. Understand one more thing I told, if this line is perpendicular to the electric field, this will be an equipotential line. If this is a plane, equipotential surface, so this line is perpendicular to the electric field. It has to be 0, or you can understand this way, delta x is 0. Fine. Delta x is 0 means from here to here, if you say delta x is there, but we are seeing perpendicular to the electric field, in the direction of electric field, or you can see this way. Forget this. Now here we are moving from D to A. This delta x is this 1 meter. E delta x cos 90. E delta x cos 90. See the angle between electric field and delta x. So this will become as 0. Fine. Either you can understand it as an equipotential line, or you can do cos 90 E into delta x cos 90, then also you will get the answer. Here, VC minus VA. VC, VA. We are moving from here to here. VC minus VA means we are moving from A to C. On moving from A to C, what will be the potential difference? Tell me. Again, if you understand, if you see this as an equipotential line, because it is perpendicular to electric field, it will be equipotential. That means VB and VC are same. VB and VC are same. So VA minus VB or VA minus VC both will be same. VA minus VB is 10. So VA minus VC will also be 10. So VC minus VA will be minus 10 volt. Clear? Or you can do one more thing. This delta x will be root 2. This angle will be 45 degrees. E delta x cos 45. E dot delta x, E delta x cos 45. This will be 10 into root 2 into 1 by root 2. Root 2 got cancelled. We are left with 10. Plus or minus, on moving towards the electric field, this C is this side of A. On moving towards the electric field, potential decreases. VC is less than VA. If VC is less and it is kept first, it will be minus. Clear? Minus 10. That's what I wrote. So either you can see it as an equipotential line, VB and VC will be same, VA minus VB is 10. So VA minus VC will also be 10. So VC minus VA will be minus 10. Or you can do this, minus E dot delta x. Or directly what we did, E delta x cos theta, and then minus sign we have put it logically, thinking that going towards the electric field potential decreases. Fine, easy. From this question a lot of concepts would have got clear, right? Alright, next. In a 3D space, V is equal to x cube minus 6y plus 3z square. Find electric field at 1, 0, 1 and also find the magnitude of electric field only. This x cube minus 6y plus 3z square is the value of V. Electric field, if we have to find out, we need to find out electric field, we know that is equal to Exi cap plus Eyj cap plus Ez k cap. We need to find Ex, Ey, Ez. Ex is equal to minus dou V by dou x. Ey is equal to minus dou V by dou y. Ez is equal to minus dou V by dou z. Correct? Here, what does this mean? Differentiating with respect to x, keeping y and z constant. Differentiate. If I differentiate with respect to x, keeping y and z constant, this will become 3x square. This will be 0, this will be 0. Plus, minus 0 plus 0. Correct? So finally it will be 3x square only. Now, here, keeping x and z constant, I have to differentiate with respect to y. This will be, okay, minus sign will also come because of this. Minus dou v by dou x. Okay. Here, if I differentiate, this will be 0, this will be minus 6. this will again be 0. Minus 6, and here a minus sign is there, so 6 will be coming. Differentiating this with respect to z, keeping x and y constant. Constant differentiation is 0, constant differentiation is 0. Differentiation of 3z square will be 6z, correct? And a minus sign is there, it will be minus 6z. Fine. So from here, I can write, okay. From here, I can write E vector is equal to minus 3x square I cap plus 6j cap minus 6z k cap. Fine. Magnitude under root of minus 3. Okay, 1 second. This is electric field in general, right? For this particular question, we have to find at 1, 0, 1. So x we have to substitute with 1, y we have to substitute with 0, and z we have to substitute with 1. So E at 1, 0, 1 is equal to minus 3 I cap plus 6 j cap minus 6 k cap. Clear? X I have kept as 1, z I have kept as 1, y is not there only. So now E vector mod will be under root of minus 3 whole square plus 6 whole square minus 6 plus minus 6 whole square, correct? 9, 36, 36, 72, 9, 81, under root of 81, that is equal to 9. That is equal to 9 Newton per coulomb. Fine. Depends on what unit we have used. Newton per coulomb. Got it? How? By knowing the potential, we got the electric field. Done? So I hope you understood today's session. Like this, there can be any question. They can give V as xy square plus zy, something like that. They can mix also. It doesn't mean that x term should be different, y should be different, z should be different. It's not a vector quantity. This is just an entire value. For E, we write as ex I cap, ey j cap, ez k cap. Right? Here also in Ex also, x, y, z, any term can be there. What does this mean? This means that x is also dependent on y. If here in Ex, suppose 3x square y comes, then see, if 3x square y will come, it does not mean you have got a wrong answer. How can y come in I cap? It simply means that x is also dependent on y. On changing y, x is also getting affected. As simple as that. Clear? So here, partially differentiation, I hope you can do. Differentiating x, keeping y constant. Then differentiating y, keeping x constant. Then differentiating z, since z is not there only, z is also there. So differentiating z, keeping x and y constant, like that also you can do. Okay? Try the questions on your own. So I hope you liked today's session. If you liked it, do press the like button. In the next session, we will be doing electric potential due to sphere. Again, very interesting session. Alright. Keep revising the things what I have taught today. This was really important, the relation between electric field and potential. Just do revise the things. Questions based on this also comes in competition. Okay. Equipotential surfaces, sometimes questions comes in board exams also. Okay. Do press the like button. Share it with your other friends who are preparing for their boards and competition. Subscribe to our channel and do not forget to click on the bell icon so that you'll never miss any update from us. We'll meet up in the next session. Till then, keep learning from We Learning. All the best.